Working now? Okay. And this work was done in collaboration with Sandra Alves and Mário Florido. So, to start, we all know that the lambda calculus assumes unlimited duplication and erasing of variables, which means that it lacks a notion of cost. And we also have substructural type systems which restrict variable usage. And so using that, we use some work by Sandra Alves and Mário Florido that relate ACI intersection type systems, that is associative, commutative and idempotent intersection types, with the Curry and relevant type systems. And also that there is a relation between AC intersection types, that is associative, commutative, and non-idempotent intersection types, with the affine and linear type systems. And here we don't want to focus on restricting variable usage. We want to see how resources are being used. And so we want to be able to relate intersection type systems to that, those calculi that track resource usage. So we are going to use the resource calculus proposed by Budal, which uses bags of resources. And here we have an example that uses the finite subset of his calculus. And here you can see that in the first reduction step, we get an explicit substitution that says that the identity function is available for usage twice. And then we substitute the x, in the first part of the application, and we cannot perform substitutions on any bag of resources, hence why the x with multiplicity 1 stays there. And so we go on, and in the end we get empty bags of resources, and so we can eliminate them because we don't need them anymore, and we get the identity function. So here we want to use a notion of expansion, which was firstly introduced by Mário Florido and Luís Damas, in order to, and they used it to transform lambda terms into linear versions of themselves. And here we want to use that notion of expansion in order to transform lambda terms in terms that track resource usage. And here we are talking specifically about the one proposed by Budal. And then we want to be able to, after transforming a lambda term into a term in Budal's language, if we reduce both, we wish that the resulting lambda term will be transformed into the resulting term in Budal's language. But there is a problem, which is that in the lambda calculus, substitution is implicit in beta contraction, which means that we cannot really track where substitution is being performed. So we are going to use a calculus that uses explicit substitutions. And this calculus, the lambda x calculus, is a variation of the lambda sigma calculus, but instead of using indices, it retains variable names. And here, explicit substitutions are given highest precedence, and it has explicit garbage collection. And here we have another example. I'm going to use the same example throughout the entire presentation. And whereas in the standard lambda calculus, we would, in one reduction step, get to the third reduction step in this calculus, that is identity applied to the identity. Here, the first reduction step will introduce the explicit substitution, and then the second step will move that explicit substitution into each part of the term. And then we get the substitution itself, and then we continue reducing, and we get the identity function. So now we have said that we cannot really start from the lambda calculus. We need to go into a calculus that uses explicit substitutions in order to prove what we wish. And so here's the question: can we relate terms typable by intersection types and each subset of Budal's language? Here we are focusing specifically on relating terms typable by ACI intersection types with the subset of Budal's language that deals with only infinite multiplicities. And this is very similar to how the lambda calculus works, because in the lambda calculus, we have a function argument available for however many times the function the variable we wish to substitute is available in the term, in M. But, and in in Goodall's language, we also get that, but we have a multiplicity of the infinite here. And it also has some operational differences. And here is a notion of expansion. I'm not giving you the entire definition because it's a bit technical. So given a pair where M is a lambda X term and sigma is an intersection type, we define an expansion as a transformation from M with type sigma to N, which is a term in Goodall's language. So here is an example, again, the same. We have a sigma, which is a type alpha to alpha. And so we are going to use our expansion. We firstly expand the first part. Here we have an abstraction. And so we will firstly expand the application and then each part of the application. Here we have an intersection type. So we are going to expand each X with, because the type of X is sigma to sigma intersection with sigma. Here we are going to expand each X, the first one with the sigma to sigma and the second one with the sigma. And then we get the X applied to X with the infinite multiplicity. And because we don't really know how many times it occurs in the term because we are working with idempotent intersection types. And then we get the abstraction, which is trivial, the abstraction rule. And then the second part, we have the identity function, which has type sigma to sigma intersection with sigma. And so we have to transform each part of the identity function. So we will expand one with the sigma to sigma type, and then another one with the sigma type, and we get the identity function as well. But in our term, this function argument, the identity function, will have a multiplicity of infinite. Okay, so we get to our theorem. Yes. Input.
Okay.
Yes. Given a lambda X term M and a type sigma such that the expansion of M with type sigma is M star, then if we reduce in 0 or more steps M to V1, and then we will be able to reduce M star in 0 or more steps to V2, and the expansion of V1 with type sigma is V2. And here, again, the same example. We have the first example I gave you with the explicit calculus, which yields the identity function. Then we have our expansion, and then we have the reduction of this term. Now this works similarly to the one I showed earlier, but here our bags aren't empty because the resources are infinitely available. But since neither Z nor X appear free in the identity function, we can remove them and we get the identity function. And so in the end, we get here that the expansion of the resulting term in the explicit substitutions calculus, is the term that results here in Goodall's language. Okay. So to conclude, we proved that ACI intersection types relate to a resource calculus that deals with infinite multiplicities. And this serves as preliminary work to something we're working now, which is relating AC intersection types, that is the non-idempotent intersection type systems, with the resource calculus of finite multiplicities. And we also wish to further on look into alpha conversion because it's not really dealt with in this calculus. But that's all.